Hi, today we're talking about the definition of the natural log, which we've actually been studying for quite a while now, and the fundamental theorem of calculus. Um, we talked about the fundamental theorem of calculus, and there are many different components of that, so this is just a different component as opposed to f of b minus f of a when we have a definite integral. So let's start with this new definition of the natural log function. So here's our definition, that the natural log is the antiderivative of 1 over t dt from 1 to x. Now, x must be a positive number. So let's look now at this property down here, the integral of the reciprocal function. So if we have the antiderivative of 1 over u du, we're going to end up with the natural log of the absolute value of u plus c. Now, why? Why do we have this absolute value? Well, let's look at the graph. So I'm going to actually start by looking at the graph of e to the x. So if I were to graph e to the x, that graph looks like this. And this y value, where the e to the x crosses the y-axis, is at 1. The graph of the natural log of x is the inverse of this. So you would reflect that blue y equals e to the x over the line y equals x, and when you do, you get this graph. And this value right here on the x-axis is now 1. And if you look at that graph, we have an asymptote at the y-axis, which means I can never take the natural log of a negative number. Negative x's are not within the domain. Okay, and that's because when you look at the blue e to the x graph, we have no negative y values. So when I look at the inverse of that, over here, we have no negative x's. So that's why we have to have that absolute value. So please do not forget that you need an absolute value when you take the antiderivative of 1 over u. So let's look back now. Sorry, I'm taking you all over the place. We're going to look back at this, and let's actually evaluate this now. So using our property, we have 1 over t dt. So that's going to be the natural log of the absolute value of t. Our bounds are from 1 to x. Okay, so I'm going to plug in the top bound, which is x, minus, and plug in the bottom bound, which is 1. But looking at your graph or knowing your log rules, what is the natural log of 1? Well, the natural log of 1 is 0. So that leaves me with the natural log of x minus 0, which is the natural log of x. And because of this statement right here, x has to be a positive number. That's why we do not have to write the absolute value for this definition, because x has already been defined as a positive value. So let's look at an example. So we have this quotient. So that's sort of your key. When you see a quotient, you want to look for a natural log. That doesn't mean every single quotient is a natural log, so you do need to be careful. So the first thing I'm going to do is I'm going to rewrite this, because I've got 1 over something. And in this case, my something is tangent of 5x. Then I am multiplying by secant squared 5x dx. Now, initially seeing that, I wasn't very happy, but now that I've broken it down, I am quite happy, because what's the derivative of my inside? My inside is tangent x, of 5x, and the derivative of the inside is secant squared 5x times 5. So that makes me pretty happy now, because I have this secant squared 5x, and that's what I want, is the derivative of the inside. What I am missing, though, is the 5, which means I can deal with this a couple ways. I can put a 5 in here with my derivative, which means on the outside of my integral I need a 1/5, or you can just incorporate it as you go. Whichever works for you is fine with me. So when I do this antiderivative, I'm going to get 1/5 The antiderivative of 1 over tangent of 5x is natural log absolute value of tangent of 5x and then plus c. Now, we can go ahead and check that, which should be pretty easy, hopefully. So we check it, the constant stays. Natural log, when I take the derivative, is 1 over tangent of 5x times the derivative of the inside, which is secant squared 5x times 5. And if you notice here, we have a 5 and a 1/5. That reduces to a 1, so I can rewrite this as secant squared 5x over tangent of 5x. And is that what I started with? Yes, it is. So I like my antiderivative, which is right here. So next one is a U try. So in this one, I do want you to actually try this before you keep playing the video. And then after you play the video again, the solution will be there. So please pause the video now. Here is my antiderivative. So what I did first is I took the top and I wrote it right here. And I'm looking for the derivative of the inside. My inside was the green 1 plus x cubed, and the derivative of the inside is 3x squared. Now I had the x squared right here, but I was missing the 3, so I added a 3, which meant on the outside, to balance out the 3, I need to multiply by 1/3. So here is my answer. Let's go ahead and give it a quick check. My constant stays. The derivative of the natural log is 1 over whatever I'm taking the natural log of times the derivative of the inside, which is 3x squared. And when I simplify that, I have 3x squared over 3 times 1 plus x cubed. And the 3's simplify to a 1, leaving me with x squared over 1 plus x cubed. And that is what I started with up here. So moving on to the back. Here is another property. So we're moving on to a different topic right now, and that's the fundamental theorem of calculus, and this is the derivative of an integral form. So what this says is if we've got g of x is some function where it's the definite integral of f of t dt from a to x. A is a constant and f is continuous, okay, within this interval. Then the derivative of g of x should be f of x. Okay, so let me look and see what that means. What I need to do is I kind of need to set up a little dummy function. So if I have that the antiderivative of f of t, I'm going to call that capital F of t. Okay, so for right now, while I'm talking through this property, the antiderivative of little f of t, I'm going to call that big F of t. So let's look at g of x. G of x is the antiderivative from a to x of f of t dt. So that's going to be capital F of t, whatever the antiderivative of, it's going to be some function. I don't know what it is. But I'm going to plug in my bounds from x to a. So that will be capital F of x minus capital F of a. Now let's remember a is a constant. So this f of a, this thing is just a number. Okay, that is just a number. Now what this property is saying is let's take the derivative of g. This thing right now, that is g of x. If you go back to the beginning, we started with this is what g of x is. So let's find the derivative of that. Well, the derivative of big F, if we go back to our property right here, if capital F is the antiderivative of little f, that means that when I take the derivative of big F, I should get little f. So that's going to be f of x. And again, f of a was just a number. When I take that derivative, I'm going to get 0. So the derivative of g will actually be f of x. So let's look at example 2. We have this thing, and what it's saying is, okay, let's find g prime of x. I'm just going to use the property at this point, and the property says g prime is just going to be f. What's my f in this case? Well, f is sine of t, which means g prime of x should be sine of x. I'm not sure if we all believe that, so let's go ahead and work it out. So if we were to find the antiderivative, we would get g of x would be the antiderivative of sine is negative cosine of t, and that would be from 1 to x. So let's plug in our bounds. Negative cosine of x minus negative cosine of 1, which is negative cosine of x plus cosine of 1. And now let's take the derivative, because I don't want g, I want the derivative of g. So I take the derivative. The derivative of negative cosine is negative sine of x, and the derivative of cosine of 1 is 0. So that leaves me with sine of x. Well, that's exactly what I got by using the property. So I buy it. I like that. Let's move on and try another one. It does get a step more difficult. So for this one, it's a little trickier than just using the property because we actually have a chain rule to consider. So I'm going to work this out first, the second way that we did, the way I did in black. So let's look at g of x. And the antiderivative of sine, we've already discovered, is negative cosine of 2t. The derivative of the inside was 2, so I also need to multiply by a 1/2. And I need to go from 1 to x squared. When I do my work, I'm going to go ahead and pull that negative 1/2 into the front. So I have a negative 1/2 cosine of 2t. I need to replace t with x squared. So that's 2x squared minus negative 1/2 cosine. Now I need to replace the t with 1, which would be 2 times 1. So when I simplify that, that's negative 1/2 cosine of 2x squared plus 1/2 cosine of 2. And again, this is g. So let's go ahead and find the derivative of that. So g prime is going to be, my negative 1/2 stays. The derivative of cosine is negative sine of 2x squared, the same thing, times the derivative of the inside, which is 4x. And this 1/2 cosine 2 is a constant, so that would be plus 0. So let's just simplify this up just a little bit. My negatives make this positive. I have a half and I have a 4, which leaves me with 2x sine of 2x squared. So let's talk about the property and where this actually came from. What's easy to see is that the x squared is simply plugged in for the t. That's simple. And that's what the property says. However, where is this 2x down here coming from? Well, the 2x is coming from the derivative of your new inside. You're replacing all the t's with x squared. Before, the derivative of t was dt. Now we're replacing that with x squared, so my derivative is 2x. So for this problem, I can jump when I know g of x is the integral from 1 to x squared of sine of t dt. I can jump to the derivative is going to be the derivative of your bound that you're plugging in that's no longer just an x. It's something involving a power rule or a chain rule. It's going to be 2x sine, sorry, there's a 2 right here, of 2 times x squared. And again, you can jump to that because I'm going to give you things you cannot find the antiderivative of. So pause the video if you need to take a moment with what happened there. So I'm going to do one more example. And this one I'm going to use the property. I don't know the antiderivative of secant t, and you don't either. So that means we have to use the property. So my derivative is going to be secant of something, That something is 5x. And then I need to multiply by the derivative of my new inside. My new inside is your 5x, which means I multiply by a 5. So this is going to be your g prime of x. So what I'd like you to do is use that concept to do u try 2. Okay, and when you, after you've paused the video and you've played the video again, the solution will be there. So right now, what I'd like for you to do is pause the video and do u try 2. Here is my solution. And again, I multiply by the derivative of my new inside. My new inside is the 2x squared. The derivative of that is 4x. Inside my t, I'm going to replace the t with my new top bound, which is 2x squared. So in my square root, I now have 5 plus 3 times the quantity, 2x squared to the 4th. So please bring any questions that you have to class, and I hope you have a nice evening.